record. Okay, so welcome to this course on convex optimization. My name is Shashank, and I'm a faculty in the EE department. So this course has a course homepage. There's also a Google Classroom for this course. Everyone who's registered will typically get the link or will be automatically added to the Google Classroom. But in case you have not been added yet, so if you've registered today or so, then probably I'll add you today. But let's say by next class, if you have not got a Google Classroom invite, then just send me an email. Okay. In case you are planning to just sit through this course and have not registered, then just send me an email and I'll add you to the classroom. All right. So much of the detail, including lecture notes, references, and homeworks, all of this will be added to this course webpage as and when we go along. So you can see that this is going to be the tentative assessment for this course. There'll be, these percentages may vary a little bit as we go along, but there'll certainly be these components. So homeworks will constitute the major component for assessment. And this attendance and class participation, I may move it to something else. But there'll be some in-class quizzes, surprise quizzes. These will be very short, very simple, just to make sure that you're following things more than anything else. There'll be a midterm exam, and there'll be a final, maybe project kind of a thing. So this course will involve a lot of math and programming, and by the end of the course, hopefully you should be able to pick up a project, solve an optimization, formulate an optimization problem, solve it on your own, and present it in the form of a report. Okay, so that's what you can expect from this particular course in terms of assessment. Grading will be relative, and yeah, so that's about it for assessment. This is my email ID, and my office is in Academic Block C, room 446. If you have any questions and want an appointment, then just send me an email. There'll also be some teaching assistants who you can contact during the course if you have any questions. Those details will be shared with you later in the Google Classroom. And yeah, so this is probably the other thing that we need to discuss, that is class timings. I did receive a couple of requests saying that this clashes with some other course. And it's going to be difficult to move the class around because of various other constraints, because there are people from different streams for whom something may not work out. And also the other issue is finding a classroom which can accommodate enough people. So how many people have an issue with this particular time slot? How many of you have class? So what does this clash with? Okay. Okay. Which one? How many of? Okay, so total show of hands. How many people have a clash with some other course? That's 5. Any more people who are not here presently? Any of your friends? How many? I want a rough number. 7 more. Okay, visual computing is an elective?
It's a elective.
Okay.
You have the choice between this one and visual computing.
Okay. Okay. All right. Well, then you'll have to suggest an alternative time slot, something that should work for everyone. So for the rest of you people, I'm assuming that this slot is okay. Is that right?
Yes.
Okay. So which streams are you from? So I'm guessing that the EE, MTech or PhD students would have a clash with wireless communication, and AI, MTech, I guess, have a clash with visual computing. Okay. So what is the total number roughly who are affected by this?
10 marks.
Okay, so 10 people are interested in visual computing as well. And EE, I'm guessing another 10 roughly. Okay. So which time slots? So which slots work? So does Q slot work for people? Not sure if Q slot is available, but Q slot you have which course? Okay. Is there a possibility that you can get the other courses moved around? How many people are there in the other course? Visual computing.
We should be like the 20 or so already registered, I think.
Okay.
And 10 more may get.
So roughly 30.
30.
How many people in the wireless communication course? No. I'm talking about like in the course itself. Roughly how many people have registered? Any idea? Okay. Okay. So just check, please see if that can be moved around, because there are roughly 80 students, 70 to 80 students who registered for this course. So moving it around is going to be a bit difficult. So yeah, we can try to work things. I'll maybe send an email. So please, at least one of you can maybe take charge. Try to also talk to the faculty who's taking the other course and see if that can be moved. Okay, so here's there's an overview of what topics will be covered in this course. Again, all of this is tentative, but roughly this will be the structure that will be followed. Lectures will be recorded, but then you are strongly encouraged to attend classes, because there'll be a lot of in-classroom quizzes and in-classroom problem solving. I'll experiment with a little bit of both conventional mode of teaching, and also some classes might be flipped. I'll record some of the classes, and we'll try to solve some problems in class, because that's an important component of this particular course. Right. So the other thing, of course, is academic honesty. So you're strongly encouraged to discuss with each other, like for problem solving, programming assignments. I mean, you learn the best when you talk to each other, when you discuss, when you collaborate and solve problems, right? But at the same time, what you submit should be your own. It shouldn't be that you're copying someone else. So it's good to discuss with each other to come up with a solution. But in all the assignments, in all the programming exercises, I expect each one of you to submit your own solutions, right? So write it on your own. So discuss each other, come up with a common algorithm, but in the end, it should be your own submission, right? And any form of copying is going to be strongly penalized. Okay. All right. So take a look at this web page later. There'll also be some lecture notes. So we'll primarily use the following material. This book by Boyd and Vandenberg called Convex Optimization. And there's a soft copy which is available for free, and some physical copies are also available in the campus library, so you can take a look. I'll also periodically upload lecture notes. It'll be in the form of one big PDF. And as and when I have any updates, I'll let you know. But you can always take a look at the latest version here. Okay. For homework submissions, etc., we'll use Google Classroom. So that will be the primary mode of submissions. Okay. Any other questions regarding the logistics of this particular course? You have to submit assignments. Yeah, you don't. I mean, there's not a lot for exams anyhow. So yes, assignment is primary. You are strongly encouraged to do the final project, but it's not mandated. Handwritten or programming, one of those two.
With any specific languages, libraries, etc.
So we will use Python. Even if you have not programmed in Python before, I'll give some tutorials, but I expect all of you to have some programming background. Should be comfortable in programming in general. Even if you're not comfortable with the Python language, that's still fine.
Any particular libraries that we are allowed, not allowed?
That we'll as and when we go along, you'll see. So even I'm experimenting. This is the first time I'm teaching this course, so I'll probably use a mix of different things. So we'll use something called CVXPy maybe, and maybe some other things as well. Any other questions?
Would all the lectures be recorded?
Mostly yes. But we'll see. I mean, the quality of the recording can sometimes be not so great. So it's there for usefulness, but don't rely on it. And also, I mean, many of the classes will have problem solving in class, which can't really be recorded that well. So I'll expect you to sort of work in groups in the classroom itself, come up with solutions and so on. Any other questions? What do you mean? How will it be?
The midterm.
In what sense? It will be a midterm.
It's a
No, it will be a problem solving. Yeah.
this group work.
I'll give more information later. So probably groups of 2 perhaps, not more than that. Any other questions?
This is the final project.
That will be the final project, yeah. I mean, I'll finalize all of that and let you know later. Any other questions? Okay, so let's start. So what is your motivation for taking this particular course? Yeah, did I hear grade somewhere? Yes, some answer.
So at least many of the AI students also understand the algorithm sheet in the end, like optimization algorithm.
Okay. Other answers? Sorry, in state estimation. So you are from control students, okay? Others? Well, ultimately, every engineering problem, almost every single engineering problem is an optimization problem, right? So as long as you have a problem, abstractly speaking, which has multiple solutions, and there is some notion of a best solution, which means that you can quantify how good a particular solution is, that essentially boils down to solving an optimization problem. Now, some optimization problems can be solved easily, some problems not so easily. And the goal of this course is to try to understand one specific class of optimization problems which can be solved very efficiently. It's a very large class, and we'll see that as long as you can formulate it in this particular format, you can solve it very efficiently, even though you have a very large number of variables and so on. Unfortunately, a lot of the problems that we encounter in practice are not easily solvable, in which case we try to simplify things and so on. And even though these algorithms although they're not convex in nature, we can still use the same theories, the same algorithms developed over here to solve those problems as well. You see that many other problems ideas can be naturally generalized to other problems as well. Right? So let's just see some quick examples of optimization problems, right? So one example is, let's take chip design, right? So what is the problem over here? You have, let's say you want to implement a processor, which may be a 32-bit processor. What kind of constraints do you have? Well, let's say that you're given a particular schematic. and the goal is to, let's say, minimize space, right? So there's always this trade-off between the speed of a particular circuit and the total space that the circuit can occupy. So the question is, how small a space do you require in order to fit this particular circuit? Should still operate reliably and so on. There shouldn't be a lot of interference. There are a lot of other physical effects that come into the picture. So in this problem, if suppose I give you two different solutions, the one natural way of measuring these two is for the same performance, what is the space that this particular circuit takes, right? So in that case, the quantifier or your objective is the space. So the space taken is what you want to minimize, the space taken, but at the same time you want to ensure that you get the same kind of performance, right? So let's take wireless communications, right? Some of you are from CSP, I hope. So what is the problem over there? You have a communication system which is essentially a noisy medium. Your goal is to design an entire system, a communication system, which lets you transmit some bits of information as reliably as possible. But at the same time, you want to transmit as many bits of information as possible per second, perhaps. But given a certain amount of resources, your system should say take only so much power. You should get a certain quality of service. Maybe probability of error should be a certain quantity, and you should utilize only these many resources. For example, the total spectrum occupied by it, and so on. So under those constraints, what is the maximum number of bits that you can transmit per second, right? Now that's an optimization problem, because the higher data rates at which you can transmit for a given set of constraints, that characterizes whether one solution is better than the other or not. Right? So let's take signal denoising, for example. Right, so you have some kind of a signal which is, you get a noisy copy of a signal, perhaps it's an audio signal, right? You have speech and there's a lot of background noise. Your goal is to remove this background noise, correct? So how do you compare two different solutions to this particular problem? If one is less noisy than the other, let us suppose that you know what the true signal is, and if your algorithm is able to make sure that the denoised signal is closer to the original signal, then it means that it's a better solution. So there is this metric of how close two signals are and whether the denoised signal is close to the original signal or not. Correct? Let's take object detection in images. Right? So that's a classical problem in computer vision. You're given an image, and let's say you want to detect whether there's a cat or not, or whether there's a car or not, whether there's a vehicle or not, right? So then, given a particular image, you want to make sure that with a certain accuracy, let's say 99% accuracy, I want to detect there's an image. Some other scheme may guarantee, let's say 97% accuracy. So this accuracy is now a metric based on which you analyze the performance of two different schemes. But there can be other constraints as well. So for the same kind of problem, your objective may be different. Let's say accuracy is not the only criteria based on which you evaluate a particular solution, right? Suppose that the amount of resources it consumes or the time taken to detect a particular object is also important, right? So now there can be different ways in which you can quantify the performance of a system. But at the same time, you have to decide. So in any engineering problem, you have to decide what is your objective. And given a particular objective, then you can come up with solutions to solve that particular problem. Right? So here's another example in finance, portfolio optimization. Let's suppose that you have a certain amount of money, you want to invest in shares. Right? How do you decide? And of course, your goal, of course, is to maximize your returns, right? So how much do you invest in each, let's say, company, so that you can maximize your returns in, let's say, 1 month? Correct. So in all of these, there is some kind of an objective, right? Now you know what the objective is. In this case, it's returns. Now, there's also something like a constraint, right? You have only a certain amount of money that you can invest. That's not unlimited, right? And how do you allocate resources in different ways in order to maximize or minimize a certain objective is the kind of thing that we are going to be looking at. So here's another example: industrial control. Right. So suppose you have a plant and you want to control this particular plant. You have some observables, and the goal is to design a control system so that the plant behaves exactly as you want. Right. And how close your control system can make the plant go to the desired behavior. Now that's an objective. Correct. So all of these are, in each of these, you can see that there is an objective function and there are some constraints. And the goal, the first part, and in many cases the most difficult part, is to identify or mathematically identify what your objective is, what your constraints are. Now, once you have a mathematical formulation for your problem, then you can use standard tools. So there are two parts in any engineering problem. One is to model the problem well enough. The second is to, now that you have a model, how do you solve this? And for most of this course, the tools that we'll try to develop is for the second part, right? So given a particular mathematical formulation, how do you solve this? Is it solvable efficiently? Is it not solvable efficiently? Right? What kind of algorithms can we use? Right? How do you show that certain algorithms are good? Right? How do you show that certain algorithms won't work well? Correct? But at the same time, we also try to see how do you formulate a problem, right? Given a completely abstract problem. The second part is what we'll focus on, but the first part also is something that we'll look into to some extent in this particular course, right? Given an abstract problem, how do you formally come up with a mathematical model for this particular problem? Right? So let's first start with the formal definition. Right? So as I mentioned, there are three main components of any optimization problem, right? Or at least the class of optimization problems that we will study in this particular course. Now, firstly, there is something that can be controlled, right? Or there's a variable that can be changed. For example, in the portfolio optimization problem, the variable that can be controlled is the money that you put in. Right? So you can decide how much to invest in each of these different shares. Right? There's a second component, which is an objective function. Right? So the first component is there is something that can be controlled, something that I'll call an optimization variable. Okay, so the optimization variable is something that can be controlled. So in the case of, let's say, the communication problem, suppose that you can control the amount of power that you can put into, say, various channels. In the portfolio optimization problem, it's more clear because it's the amount of money that you can put in, right? Or in the case of, let's say, building a circuit or implementing a circuit on chip, maybe you can decide where to put the various transistors and where to draw the lines, right? So all of these are variables. The second thing, what you want to minimize or maximize, is an objective function. Right? So in the case of portfolio optimization, it's the returns that you get. In the case of chip design, it is the total amount of space occupied by your circuit. In the case of, let's say, wireless communication, it is the data rate at which you can transmit. Okay? The third quantity is you always have some set of constraints, right? For example, in the communication problem, it could be the total amount of power that you consume, the total bandwidth that you utilize. Right? And you always have to design your system or come up with a solution which strictly adheres to these constraints. In portfolio optimization, it could be the total amount of money that you have, right? So now how do we model each of these particular quantities? Right? So there's an optimization variable, and we typically denote this by a vector. Okay, so it's a vector in some space. So just a word of notation over here. So small letters with an underline are going to denote vectors, okay, of an arbitrary size. So let's suppose that this vector x, the optimization variable that I can control, in this course we'll typically take them to be from Rn. So the real vectors of length n. All right, and there'll be an objective function. For now, let's call it f. Okay, this will be a function which takes as input a vector, and it gives a real number. Okay. Now you also have a set of constraints. So maybe I have some g1 of x could be less than or equal to a1, g2 of x less than or equal to a2, and so on. Right? So formally speaking, I can define a minimization problem in the following way. Our problem is to obtain, in some sense, a best solution, if one exists, x star, which is that x which minimizes f of x under certain constraints, and these constraints will be modeled as g of x less than or equal to 0. Okay, where this g of x is going to be basically a vector. So it's g1 of x. So this underlying g of x is basically g1 of x less than or equal to 0, g2 of x less than or equal to 0, and so on. So I can have multiple constraints. Okay, so there's one objective function, right? One real valued objective function that I want to minimize. I can have multiple constraints, and these constraints are going to be in the form of these inequality constraints. And the input, the variable that I can control, is going to be a real valued vector. Right? So this is going to be the problem. It's, again, I've defined just an abstract problem for now. This is going to be the problem that we're going to try to solve. Now you may ask, okay, is this definition general enough? Yes.
What is the star?
So x star is, so that's the x star is the value of x which achieves the minimum of this f of x subject to these constraints. Okay. So I'm not just interested in finding the minimum value of f of x, but I also want to find the minimizer of this particular function f of x. Okay. So we'll try to look at this problem in different ways. One is, of course, trying to just come up with an algorithm which solves this particular problem. But you also need to develop a certain intuition to this problem itself, right? What do the constraints look like? What does the function look like? So all of this has a very nice geometric interpretation, a nice geometric meaning, and visualizing this can help you come up with better algorithms potentially. All right. So again, the question is this definition general enough? So I've defined a minimization problem over here, and I'm claiming that if you can solve this particular problem, then you can solve many other problems as well. Okay, so let's try to see what kind of problems can be solved and what kind of problems cannot be solved. Okay, suppose I can somehow, given any function and given any constraints which are in this particular form, I can solve this problem. I have some black box which gives me the value of x star. No matter how complicated this function f is, no matter how complicated these g1, g2, g3 functions are. Okay, as long as I can represent it in this form, I can solve the problem. Okay, again, hypothetically speaking. So now suppose I instead give you a maximization problem. My goal is to maximize f tilde of x subject to constraints, say g of x less than or equal to 0. If I can solve the original problem, can I solve this particular problem? Can I cast this particular maximization problem as an equivalent minimization problem? Yeah, exactly. So instead of looking at f tilde of x, I can just set f of x to be equal to minus f tilde of x. So maximizing f of x is the same as minimizing minus f tilde of x. Correct? Is this the only way you can do this? Yeah, I could have taken 1 upon f of x, f tilde of x, right? So maximizing f of x is the same as minimizing 1 over f tilde of x. Right? Any other solutions? Yeah. One by? That was the solution that was just proposed, right? So you can either take minus f of x, I can take 1 by f tilde of x. Anything else?
E power minus.
So this e power, I can take e to the power minus f tilde of x.
Some arbitrary function.
Yes.
Some h of f of x. That
Okay.
has certain properties.
What properties?
Should be monotonically decreasing.
Exactly, right? So I can take any monotonically decreasing function h, and maximizing f tilde of x is the same as minimizing h of f tilde of x. Correct? And you'll see that in certain problems, the choice of h can also matter, right? Sometimes just taking minus f tilde of x may work out, but using a slightly cleverer h of x can sometimes can help you in coming up with an easier solution. Okay. Now again, all of that is an art. There's no reason why it should be done in one particular way. So that's why optimization is not just a science, but it's also an art. Right? Formulating it in the right way, in a way that you can solve it easily, it's an interesting problem. Right? Okay. So therefore, if I can solve that minimization problem that I had, then I can solve any maximization problem with a similar set of constraints. Okay, but now if the constraints look a little different, then what do I do? Right? Suppose I want to minimize, say, f of x, but now I have two constraints. The first constraint is g1 of x is greater than or equal to some alpha 1. And the second constraint is g2 of x less than or equal to alpha 2. Remember that my original problem was minimization of a particular function f of x subject to constraints that g1 of x is less than or equal to 0, g2 of x is less than or equal to 0, and so on. Can I pose this particular problem in that standard form that I have?
Yeah.
Okay, yeah. So then this is the same as minimization of f of x subject to, what should the first constraint, how do you rewrite the first constraint? minus g1 of x plus alpha 1 is less than or equal to 0. The second constraint would be g2 of x minus alpha 2 is less than or equal to 0. Right, great. So it means that any sort of, as long as I have a bunch of inequality constraints, I can again bring it down to this standard form that I had represented. Okay. Now what if I have an equality constraint? Right? Maybe I have g1 of x less than or equal to 0, but g2 of x equal to a, or g2 of x equal to 0. Yeah. Sorry. Okay, so how would you do that? So this is minimum of f of x such that the first constraint is fine, less than or equal to 0, and then what do you need mod g of x? Okay, fine. Yeah, so ultimately in the standard form, what would it look like?
Gx less than equal to 0 and minus g.
Exactly. So in other words, this constraint over here is the same as g2 of x should be less than or equal to 0 and g2 of x greater than or equal to 0. So any x which satisfies both these constraints satisfies g2 of x equal to 0. Right? That's the only choice of x which satisfies both constraints. Right? Is everyone agreeing with this? Okay. So now if you have an equality constraint, then you can always write it as two inequality constraints. So g1 of x is less than or equal to 0, g2 of x is less than or equal to 0, and minus g2 of x is also less than or equal to 0. Right? Any questions? Okay. So now suppose I have a strict inequality constraint. So I have a minimum over all possible f of x subject to the constraint that g1 of x is less than or equal to 0, but g2 of x is strictly less than 0. Right? Remember that the inequality constraints were always some g of x less than or equal to 0.
Necessarily that the convex function needs to solve the zero constraint.
I've not talked about convex functions at all. I have some function f, I have some functions g1 and g2.
G2x plus epsilon less than equal to 0 for some positive.
Okay, then you need to give me another constraint for epsilon, right? You can introduce new variables if you want, but I need inequality constraints.
Tending to 0.
I want it in that particular standard.
Minus g2 of x.
Sorry?
Minus g2 of x.
But that's not the same as g2 of x strictly less than 0, right?
Minus the gx.
Minus 1 by g2 of x. Why do you say that this is okay? Is it true for all g2?
This alone g2x is 0 the whole function.
That's not the formal way of doing things. I mean, even if it's strictly less than 0, this constraint, is it the same as this constraint? Yep, any suggestions?
So I can find some arbitrary function that has a constraint and that function is a function of g. Try to optimize for the try to find that function.
Okay, so let me pose an easier question. Okay, suppose let's take a concrete example. Okay, my goal is to minimize f of x subject to the constraint that x is strictly less than 0. Okay, here's a concrete constraint. Okay, good, one single example of a constraint. So this is the constraint, right? So set of all x such that x is strictly less than 0. Can I bring this constraint down to the standard form?
Can you write it as x less than or equal to 0 and x not equal to 0?
No, I want to. So the only sort of constraints that I'm allowed is less than or equal to 0. Some function, you can choose the function as you want. If you want, you can add additional variables, I don't care. But all of these should be in that standard form. Some g of x should be less than or equal to 0. It's less than or equal to 0.
Could you say as alpha is equal to beta and alpha is equal to beta?
Sorry, you have x plus alpha is less than or equal to 0, okay?
Alpha is less than equal to.
Okay.
X minus alpha is very important.
Okay, x minus alpha, you want to say x minus alpha is less than or equal to 0, where
So the function cannot, so how are we going to change this? Alpha is constraints that the function cannot take a value of x is equal to 0. Right?
okay, maybe one at a time. Okay, yeah.
This is a simple question here.
Yeah.
Like, as per the definition, the constraint is x should be less than 0. It cannot be equal to 0 at any point of time.
Yes.
But in the original form that you provided,
Correct.
you are putting the constraint in such a way that the value can be less than or equal to 0.
Okay.
So it cannot be transformed. Like you are constraining yourself, it will be always be less than 0. It
Okay.
can be transformed.
Okay, can you give a more?
The constraints have to be mathematically defined.
Yeah, of course.
X minus maximum of x less than equal to
X minus maximum of x. Okay, that's a, what do you mean maximum of x?
Alpha multiplied to minus x. That's one.
Yeah.
Consider an alpha greater than 0 such that x plus alpha is 0. Then z is equal to x plus alpha, and z is equal to 0, we can write z less than equal to 0 and minus z.
So coming back, you want alpha to be strictly greater than 0? So that's a constraint I can't represent in the standard form, right? Okay, so here's someone who says that you cannot bring it down to the standard form. How many of you think it cannot be brought down to the standard form? Show of hands. Cannot be brought down to the standard form. How many of you think it can be brought down to the standard form, but there's some tricky way to bring it down to the standard form? I mean, raise your hands up, come on. Okay, the rest, not sure. Okay, So let's see, I think two people said that it cannot be brought down. Can you reason out why it cannot be brought down?
I mentioned if you look at this particular function,
Okay.
they're clearly giving the constraint that x cannot be equal to 0. It can be infinitely small, but
Okay.
it cannot be equal to 0.
Okay.
But in the standard form, we have already said that the value, the constraint value can be equal to 0. So there is a mismatch happening there itself. There is
Can you say that more formally? Okay. Do you want to say why? Why do you think it cannot be brought down to standard form?
looking at it, this problem cannot be fitted into the standard form.
Yeah, but why? I need a strong one. Right?
Maybe the function is not defined for x equal to this.
No, there's no. It's x, right? The function is x.
Something like f of x, the value.
No, I'm not saying. So f could be f is defined everywhere. F could be defined everywhere. But this is my constraint, right?
Okay, maybe the set has to be open, closed and not open.
Yeah.
I mean, all the values x can take,
Uh-huh.
it has to form a closed set.
Okay, very good.
Yeah, so if you have to form an open set, then I'm guessing that has to something like that.
That's true, right? So basically, the sort of constraints that you have over here are all less than or equal to constraints. It's a subtle point, but this essentially defines a closed set, right? Whereas this particular constraint that x is strictly less than 0, this basically gives you an open set. Correct? In this course we'll also try to formally define what an open set is, what a closed set is. So this particular formulation, it doesn't handle all sorts of maximization or minimization problems. So it has to come, you have to be able to formulate it in this particular form in order to, let's say, be able to solve things. And there's a reason why we are setting up these constraints in this particular form, that it forms a closed set. And we'll see that later. So one sort of the big picture of why we want less than or equal to constraints rather than strictly less than constraints is that we want to be able to, so this should have a solution, right? Or in other words, you should be able to achieve the minimum. For example, let me take the following problem where I have, let's say, x square. My f of x is x square, and my constraints are, say, x is maybe less than -1. Okay. So the constraint is x strictly less than -1. The function is f of x equal to x square. What is the minimum? Yeah.
Closest to -1.
Okay, what does that mean, closest to -1? Which point is closest to -1? Yeah, correct. So this does not have an answer, right? So the minimum does not exist. Correct? So in this case, you define something called an infimum. So the infimum of this particular function does exist, and the infimum would be equal to 1. Right? So -1 square is 1. And so it's mainly to avoid these sort of situations. So we look at nice problems where the constraints are closed, they're convex, and so on. And there's a reason for why we're imposing all of these particular conditions. Okay, any questions?
Can there be certain cases where, so if the constraints are not met, for example, if we take the G2 example,
What example?
the previous example that we had, yeah, this one.
Okay.
So in this case, we can have situations where, can we have a situation where we reach the minimum value of f of x? So say we have reached the minimum plateau of f of x, but then the g2 of x constraint may not be satisfied anyway. So would that be a
Correct. So again, maybe maybe to rephrase your question, it's possible that in this particular scenario, this was an example where the minimum did not exist, right? But on the other hand, if I had instead imposed the constraint that x is strictly less than 1, right? So in this case, the minimum is well defined; it exists, right? It's equal to 0, correct? So there are situations where this particular thing does happen, but what we want to do is try to develop a more general theory, right? In this case, in this special case, this is the same as I could have converted this to a closed constraint, x less than or equal to 1, and still ended up with the same minimum, right? The solution to the problem is still the same. The problem is different, right? Because I've tweaked the constraint in a little bit, but the solution is still the same, right? So that is why we always want to formulate it in a way such that the constraints are closed and convex. Okay, and that's mainly because some of the theory and algorithms work only for closed convex sets. Okay, we'll define closed, convex, and so on later on, but all of you have probably at least have an intuitive idea of what each of these things mean.
Coming to that point,
Yeah.
what if we divide the intervals in a way that the optimum is achieved in the particular constraint which satisfies the original one?
I'm not sure I
Like
follow.
in this particular case itself,
Yeah.
what if we define the constraint as x is less than or equal to 0, union x is between the range of 0.
Okay, but what if the solution is,
No,
again,
I'm saying,
we're boiling down to the same problem, right?
right?
So it comes down to the same problem, right? So if it was strictly less than -1, then the minimum does not exist.
No, in certain cases, I'm saying.
Correct.
In certain cases,
Yeah.
to his point only,
Correct.
like what if we divide our constraint in certain intervals that we are completely shown that not satisfying constraint is not going to give us any optimum.
So, for example, maybe to rephrase what you just said, perhaps suppose I have x less than 1, and I could say that I divide it into x less than or equal to half, in which case I have a minimum, which is equal to 0, and then argue that in the other constraint where x is between half and strictly and 1, it's always going to be greater than or equal to this.
Yeah. Or possibly if we can prove that minimum cannot exist.
Correct. So again, those are problems you could potentially look at. I'm not saying that you cannot solve such problems. We are going to look at problems which can be expressed in this particular standard form. Again, this does not include all possible optimization problems, right? But this is a class of optimization problems that we are going to look at, for which there is a nice theory. Again, we are going to impose more constraints as we go along. The f is going to have to be in a certain form, and it has to satisfy certain properties. The g1, g2, g3, and so on also have to satisfy certain properties, right? But again, in principle, you can formulate these and even more complicated problems. There's no reason to just look at minimization problems. You could look at more complicated problems where you have multiple variables, there's a tension between variables. You want to minimize with respect to one, maximize with respect to another. There could be multiple objective functions that you want to optimize over, and so on, right? So this does not include all optimization problems. That's something I want to make very clear, right? But this and a subclass of these problems are what we are going to actually try to solve. And in any case, this is a large class already, and a lot of the problems that we want to solve in practice can be brought down to this particular form. All right, any questions?
That means if you have closed set constraint,
Yep.
then the problem is solvable for sure.
Yeah, if it is closed, then there exists a solution.
Always.
And we'll see that as we go. Again, depends on f also, but yes. If it is open, then you're not guaranteed of a solution. In many cases, you will not have a solution. So again, if it is closed, I'm not saying that you can find the solution easily, right? For most nice functions, as long as it is not pathological, there will exist a solution. Okay, so now that we have this sort of general form, right? We have a standard form for a minimization problems. Let us look at some concrete examples and see how we can formulate these in the standard form. Okay, so again, to build intuition and actually make sure that we are trying to solve something worthwhile, we will look at a lot of examples, right, and see how we can solve each of these. So I'm assuming that all of you have taken a course in matrix theory or linear algebra, in which case you would have seen the least square solution for a system of linear equations, right? So let's take a general system of linear equations. So let's take a times x equal to b, right? So when can you solve this system of equations? Suppose A is a general, I have m equations in n unknowns. Yeah, okay, B lies in the column space of A, or what's another way of saying the same? When under what conditions will B lie in the column space of A?
Rank of A has
Rank of A is equal to rank of A is equal to n. Is that sufficient? Necessary? Okay, what is a left inverse?
some matrix where when the multiplier with A is I.
It's an m by n matrix. Okay.
The K cross, so the n cross m.
Okay.
Say B. So we have BA equal to IN.
B. I mean A. B. Sorry. Okay. So you mean a capital B?
Yeah.
So B times A.
Equal to IN.
Okay. So what are conditions on n, m and n? You just had to distill it down to conditions. So for example, if m is strictly larger than n, can a solution exist?
Yes.
Can it exist? So again, we're looking at necessary conditions and sufficient conditions. So if m is greater than n, can a solution exist? I'm not saying does a solution always exist.
So what about B? It can,
Which,
can exist.
for example, if m is greater than n,
It can
okay,
exist.
is there some A and some B for which a solution exists?
Yes.
So it can exist. Does it always exist?
No.
No. So m greater than n, is it a necessary condition or a sufficient condition for a solution to exist?
Sufficient condition. Either. It's neither sufficient nor necessary.
Yeah. And what would be a necessary condition for a solution to exist? Just in terms of m and n. Okay, fine. Right. So now suppose that m is strictly less than n. Okay, I have a fact matrix. Then
Solution may or may not
It may or may not.
okay, it may or may not exist. But okay, in both of these cases, what can you say about the solution space? If m is greater than n, what does the solution space look like? How many solutions can there exist?
one.
One or zero. One or zero.
So if m is greater than n,
Max one.
At most one solution.
right? So the number of solutions is either 0 or 1. If m is strictly less than n, then
Solution exists, then it will be many solutions.
so how many?
Infinite.
So the number of solutions can be either infinite or
Zero.
0
Or one.
or 1.
No.
There won't be a unique solution. Everyone agrees?
Yeah.
Okay. So now suppose that m is greater than n. Okay, and there does not exist a solution. Okay, but I still want to find the closest, in some sense. I want a closest solution to this particular problem. There does not exist a there does not exist a solution which satisfies these equations. But I want to make sure that they're at least approximately satisfied. Okay. So one way of setting this up is that I want AX to be as close to B as possible. Okay, does that make sense? So let's say I want an X such that AX minus B. So I need a measure of how close one vector is to another. And one way to look at this is take the 2 norm square. Everyone has seen the 2 norm. So my goal is to find an X for which this is as small as possible. So this is the least squares solution that you would have seen in your matrix theory course. So now I have this objective function f of x, and I want to minimize this. Do I have any constraints?
You can have the, all the values, right?
Sorry, yeah.
All the vectors x can possibly
So x is in
So you just say the norm of x minus norm of x has to be less than or equal to 0.
minus norm of x should be less than or okay, fine. You don't necessarily have to impose any constraints. So no constraint is the same as taking all possible x, right? So all x lies in Rn. So this is an example of an unconstrained minimization problem, right? So find minimum of f of x, correct? And do any of you recall what the solution to this is? Okay, do you have an expression? Okay, so it's pseudo, and in terms of A, do you have an expression for pseudo inverse of A? So x star is equal to, again, all of this is true in what condition? In what case? Yeah, so the rank is equal to at least n. Sorry, it's equal to n. Right, and do you recall how you came up with this solution?
with respect to x,
Okay,
and equal to 0.
okay, fine. So that's how you did it in class. Okay, so this is an example of an unconstrained minimization problem, and you use some properties of functions in the sense that you found the stationary point, and that stationary point essentially corresponded to the minimum. Correct? Okay, now suppose I have some particular problem where I again want to solve this least squares problem. my f of x is still ax minus b squared, right? But now perhaps I have some other constraints. Maybe I want, say, the norm of x for whatever reason should be less than or equal to 1. Okay. So I can add any number of constraints to this particular problem, and this is what is called a constrained least squares problem. So there are certain applications where you want, say, the 2 norm of x to be less than or equal to 1. Sometimes you want, say, the sum of the absolute values of the components of x to be less than or equal to some specified quantity. Sometimes you want to look at solutions where the number of non-zero entries in x is bounded by a certain quantity, and so on. There are a bunch of other constraints that you can impose, right? So in this case, this is a problem that you have seen in your matrix theory course, and you can get a closed form expression for this particular problem, right? But as soon as you impose certain constraints, right, you may not have such a nice closed form expression anymore, right? And that really brings in the challenge. How do you solve general constraint problems? The objective function may still be the same, right? Without these constraints, we know exactly what the solution is. But now, as soon as I impose certain constraints, I run into a problem. So what, if you can think of it geometrically, what could the problem be? Right? Why can't I just take f of x, try to minimize, try to find the stationary point and just be done?
The stationary point may not be the constraint of it.
Correct, right? So if the stationary point luckily happens to lie in the set of constraints, then I'm done, right? I don't have to look any further because that's the minimum without any constraints imposed. So even if I impose any other constraints, it's not going to change, right? So if you think of it visually, right? So I have some kind of a function, right? Suppose that there is only one stationary point and that corresponds to the minimum. Someone tells you this, okay? This may not always be the case. But suppose there is only one stationary point and this lies in the set of constraints. So this stationary point satisfies all the constraints that you have, then all is well and good. But now suppose that it does not satisfy the constraints. Then what do you do? Okay. Can you speak up a little?
Is there another constraint from?
Okay.
Sorry.
Okay, but how will you solve?
First, we didn't get a solution.
Mm-hmm.
So based on the
No, I mean solution in the sense that right now the solution, the way you know how to solve this is you take f, you differentiate it or find the gradient, set it to 0, right? And that gives you a point, that gives you a stationary point, correct? If the stationary point, I'm again giving you this information that if there is a stationary point, it's a point of minimum, okay? I'm giving you this information. Now you evaluate the stationary point, you find the stationary point and see that the stationary point does not satisfy the constraint, okay, for this objective function that I've given. Then what do you do? What can you say about the solution?
So the norm of the x actually denotes like a Euclidean point in the space, right?
Okay.
So we can take a point in x
Hmm.
that will be closer to the particular function here.
Okay.
So the closest point kind of represents like a minimum.
Okay. Yeah, you're kind of trying to get some intuition, but that's not always true, right? The closest point doesn't necessarily give you the point of minimum. The point with the minimum gradient that need not give you the point of minimum always, right?
That constraint, right? With the amount of the constraint.
So here's sort of an example. It's not a very good example, but suppose, so you're saying that the point with the smallest gradient,
Smallest absolute rate.
the smallest absolute gradient. Okay, so the point of the smallest absolute gradient you're saying is going to be the point of this, right? So suppose I have this weird looking function where it's something like this. Okay, and suppose that the constraints say that it has to lie within this particular set. The point of, so the minimum point is here, right? Whereas the point of least gradient will probably be this. Yeah, probably this somewhere over here, right? So in fact, the right intuition is that in general, if it's not this point, it's going to lie somewhere at the boundary, right? And why is that? It's because if that's not the case, then that point would be the absolute minimum. So that's why we'll try to build intuition as we go along the way. So geometrically, what happens if you have, say, functions which are smooth, which look convex? So in this particular example, right, I've drawn this particular curve. So when I impose certain constraints, what exactly am I doing? I'm restricting the set of X, basically my search space, right? Earlier it was the entire real line if it was in one dimension. But now when I impose certain constraints, I'm saying that X has to lie within a certain set, whatever that set may be. It may look weird, but suppose that the X lies in an interval, right? So for example, it could be this particular interval. It could be a union of intervals for all I know, correct? But if it is an interval, then what I can guarantee is that in this particular interval, as long as they're, let's say, to the right of the minimum, it's going to be continuously decreasing. Again, in this example over here. And therefore, the point of minimum is going to be one of the extreme points. Similarly, if it's to the left, it's again going to be an extreme point. Okay. So we'll
only if the function is convex.
Only if it is convex, yes. Yeah. Otherwise, things can be wild. Right? I mean, if the function is non-convex, even if you don't have any constraints, finding the minimum is not always easy because there could be multiple stationary points. Right? Just setting the gradient to 0 does not necessarily give you the point of minimum. So we'll analyze all of these as we go along. All right. Any questions so far? Yeah. A stationary point is one where the derivative is equal to 0 if it's a function of one variable, or the gradient equal to 0. Okay. Again, we formally define all of these, but you've at least heard of. You should be at least familiar with this. So a stationary point is just a point where the derivative equal to 0 or the gradient is equal to 0. Yep.
So are you saying that with this particular constraint of norm of X should be less than or equal to 1?
Yeah.
You can only find it when it is a convex function.
I'm not saying that you can solve this problem only if it's a convex function. I mean, you could solve it for other functions as well. But the point is that if everything is convex, as we'll see, there is an efficient way of finding a solution.
Like we do not, so X I believe is an n-dimensional space. So we know that since it's a metric equation here, it will be a kind of like a hyperparabolic equation, like that.
In this, okay.
Yeah. So in that particular one, how can we say that a particular weight value can be easily found in that way? Because in two-dimensional space, we can easily measure that. Yeah. But
it is not, yeah, it is not trivial to say that you can solve convex optimization problems easily, right? That is, it is in some senses a surprising statement, right? And again, we had to see what we mean by efficiency and so on. Right? In principle, a solution exists. That is something that we can always guarantee. But again, how do you find it efficiently? What do you mean by efficiency? That's something that we will explore. Any other questions? Okay. All right. So let's take an example in communications. Right. So have any of you taken the information theory course?
Started.
Okay. Ongoing. Okay. All right. So one again, as I mentioned, the communication problem. The goal is to somehow design a system for which you can transmit at a high rate while satisfying some set of constraints. Okay, so one problem in information theory is, suppose I have multiple channels, so to speak. I have a total power budget and I can allocate power over these different channels. Now these channels are not identical. They're all noisy channels, but they all behave in a certain way, right? So I have these different channels. So each channel is basically the following form. If I transmit, say, a real number, at the output I get a real number, but it's going to be corrupted by noise. So it's y1 equal to x1 plus z1, y2 equal to x2 plus z2, where I can transmit any real number x1, x2, and so on. The receiver is going to see y1, y2, and this is Gaussian noise. So each zi is Gaussian with zero mean, and this has variance sigma 1 square. And over the second channel, this is Gaussian with mean 0 and variance sigma 2 square, and so on. I can have multiple such subchannels. Okay. So let's not bother about how this comes about and so on. But let's say that someone gives you this abstract thing, which is like a black box. Okay, so you have these multiple channels and your goal is to transmit data across these channels. Now I have a total power budget. So my x1 square plus x2 square and so on. Say I have m channels, xm square should be less than or equal to some power constraint P. All right. So basically I can allocate a power of P1 over the first channel, a P2 over the second channel, so on, Pm over the mth channel. Okay. Now I need to know how, of course, so one might assume that, okay, I find the best possible channel and I pump in power completely over that particular channel. Right? That's something that you might expect or think that that's the best thing to do. But it turns out that that's not the best allocation. Right? It turns out that if you look at the total data rate, the data rate over the ith channel turns out to be the following function. Right? So the total data rate, or the data rate over the ith channel, turns out to be half log 1 plus pi by sigma I square. Okay, so this is sort of a limit on how much data rate you can pump in over one particular channel. Right? So if you're taking the information theory course, you'll see this later on. But if you're not, it doesn't matter. Let's assume that I'm giving this to you. Okay, so this is the total data rate that you can transmit over this set of m parallel subchannels. Okay, my goal is to maximize this. Right, so this is the objective function, and even though, I mean, if you look at it, you may think that the best solution may be to just pump in all the power to the best subchannel, that is the channel for which sigma I square is the minimum, but the solution is a lot more complicated than that, right? So again, this is a constrained optimization problem where this is your objective function f of x, or in this case f of p1, p2, p3 up to pm, and your constraints are that p1 plus p2 so on up to pm should be less than or equal to p. You can again bring this down to standard form, so that boils down to minimizing minus r subject to the constraint that p1 plus p2 plus p3 and so on up to pm minus p is less than or equal to 0. Right? This is one of these few problems for which you can actually obtain a closed form solution. Right? If you've seen Lagrange multipliers before, then you can solve this using Lagrange multipliers, and that is indeed what you will do in the information theory course. Okay, so there are these different kinds of problems. Each of these look different. We are sort of adding layers of complexity. We started out with an example of an unconstrained minimization problems. Then we have some certain constraints. Some of these can be solved. You can get a closed form solution. Some of them can't be. You can't get a closed form solution, but you can still solve numerically. But then we'll also see some problems for which you cannot obtain closed form solutions, and you can't even solve them numerically very efficiently. Right? So maybe let's stop over here. There are only 5 minutes left. All right. Any questions?
Material for this which was given.
For these examples, again, Boyd doesn't have these examples, but you can look at the lecture notes that I have posted.